All right. So we are going to close chapter 3 with the final extension to three-dimensional linear systems. So we have done so many things in two dimension. Now we want to extend it to three dimension and higher dimensions. So basically, what do we have here? We're still focusing on anything that can be written as y prime equals ay. But before this, a was 2 by 2. Now we say, well, this a can be 3 by 3, or even eventually n by n. Okay, where are we going to get those? Well, you can easily think about a problem which involves 3, and make sure that they all have constant coefficient. Okay, and then you can easily rewrite them into a format. Prime equals 2, 1, negative 1, 3, negative 6, 2, 0, 0, 1. Okay, so from here you can see it's very easy to write them into a three-dimensional system in terms of matrix format, as long as they all have a linear coefficient. Even though they are not constant, what you're going to have is some function here. But for now, we just focus on this. Okay, so which means your matrix does not depend on t. How do we analyze it? Well, how do we analyze two-dimensional problem? We found lambda, we found v, eigenvalue and eigenvectors. Through there, we started to see like, okay, what kind of a solution looks like. We may have straight line solution, two distinct real. We can have one straight line solution, which is parallels, where you have zero eigenvalues, you have two complex values, we have all the cases. In three dimension, it's the same thing. So, first thing is eigenvalue and eigenvector. And we have done this in calculus, in linear algebra before. When we do eigenvalue and eigenvectors, we don't have to do a 2 by 2 system. We can do an n by n system. The analogy is still, the steps are still doing this. And we do know how to compute a high-dimensional determinant. We still set them to be 0, and this is still going to be a polynomial of lambda. 2 by 2 is a quadratic. 3 by 3 is a cubic. The higher you go, the higher the polynomial, but eventually it's going to be a polynomial. And because it's a polynomial, you try to solve the root of polynomial, we know we can only have two possible cases. The first one is going to be we are going to have real. And second, we are going to have pairs of complex. The pairs of complex come from irreducible factors, and the real come from linear factors. And for real, you can further differentiate them into zero eigenvalues, okay, distinctive eigenvalues, and the repeated eigenvalues. Okay. It's just this time we have more than 2. We have 3. And then we just need to figure out what's going on with each one. And pretty easily you can imagine the idea generalized. The pair of complex always give you something with a spiral. Okay? You still look at the real part to see, do you have a spiral source? Do you have a spiral sink source or center? Still the same thing. Now for real, for 0, you still have this case. For repeated real, you still have this case. Coming in or out. And for distinct, you still have straight line solutions. It's just this time maybe you don't have 2 straight line solutions. You may have 5 straight line solutions for higher dimensions. Each one give you eigenvector, and just follow that direction, you are going to have things like this. So you can analyze three-dimensional systems as long as you can calculate the eigenvalue and eigenvectors. Okay. For example, let's do some analysis for three-dimensional system. What are the possible cases you can get? You are going to have 3 eigenvalues for sure. Then there are several possible cases. You have 3 distinct real. Okay, what's gonna happen? Then you are going to have one direction of your straight line solution. You have another direction of straight line solution, and you have another direction of straight line solution. Depending on each lambda is positive or negative. If it's negative, it goes in. If it's positive, it goes out. If it's negative, it goes in. Okay, so you have 3 different directions. Each direction you have straight line solution. Now, do you have a sink? You require everybody to actually come to the same thing. come to 0, 0. That means all lambda less than 0 give you a sink. All lambda bigger than 0 give you a source. Okay, some of them are positive, some of them are negative. That give you something which is a source in some direction, which is a sink in some other directions. It may be 2 sink, 1 source. It may be 1 sink, 2 source. Okay, as long as they're not all source in all directions or all sink in all directions, they're not going to be a source or a sink. So that's 3 distinct real. What else? You can have 1 real and another repeated real. Okay, that's going to give you 3 dimension. In 1 dimension, it's going to be the real. It may be a sink or source. Then in the other direction, you are going to have something which we had before. That is, you are going to have something in this plane going like that, going like that. Okay, in the horizontal plane, but in the other direction, which is vertical, which I draw as a z-axis, you are going to have something got attracted. And so the whole thing is going to spiral, but spiral down. Okay, so if you really want to draw it, it's going to be something. Starting from here, if you look from above, it's going to be exactly as the same before, but now it actually spirals down because in the z direction, you are going down like this. Similarly, you have something from the bottom, but it goes up. Okay, that's going to be what you have for this case. And again, it's very possible you can have 1 real repeated for 3 times. Repeated for 3 times. Okay, what's going to be that thing look like? Well, you are going to have 1 direction, which eventually, when you let t goes to infinity. By the way, if you have something repeated for twice, you take this one and you take this one. If you have something repeated for another time, you are going to take another one in order to form the 3 solutions. Okay. From here, you can see you will have 1 direction when t is big. Everybody is roughly in this direction. So you are going to have this 1 direction. And no matter how you start, eventually you go into that. Okay. This is a 3D dimension. It's really difficult for me to draw. So try to imagine what's going on to your best knowledge. To your best knowledge. So this one does not have to come from this plane. It can also come from this plane. Okay. If I somehow can draw a thing like that, you can try to see they are not actually in the same plane. Okay, this can still happen. All right. Now number 4, you can have what? You can have 1 real and 2 complex. Remember, complex can only appears in pair of 2. So what's going to happen? Well, it really depends on, do you have a real? This real is negative or positive, and the 2 complex, do they give you a source or do they give you a sink? For example, if you have a sink for the 2 complex, okay, and you have for the real one, you have lambda less than 0, then everybody is going to be attracted to this in that real direction. And then in the complex direction, it's going to be spiraling in. This is probably not intuitive. Let me see if I can draw it. So you will see a curve. It actually rotates as a spiral sink if you look from above, but meanwhile it's actually going down in the vertical axis, okay, which is in the direction of the real, according to what I draw here. You can also have a source combined with something leaving or something coming in. You will have all kinds of different cases. Okay. From here you can see the analysis still works. And if you actually project some of the eigenvalues onto some kind of eigenplanes, some kind of planes, you will start to see, okay, they are exactly the 2D case. Okay, to see example, let's just try 1 example. Let's not do this first. So this is what I do. Okay, I pick a 3 by 3. I calculated the vector, eigenvector. I calculate the eigenvalues. From here, you can see you have one real eigenvalue, which is -3. You have two complex eigenvalues. They appear in pairs, and their real part is less than 0. So in this plane formed by these two complex eigenvalues, you are going to have a spiral sink. Meanwhile, in the direction of the third, you are going to have a attractor, a sink. Then, from here you can see, if you just look at the xy plane, which I draw here, it's a spiral sink. Meanwhile, as you spiral sink towards 0, 0, you also goes down towards 0, 0 because of the -3 in the real direction. So this is what your trajectory looks like. From here you can see it's already very difficult for you to see the direction field. Okay. That's why we say, well, when the graphing is not reliable in 3 dimension, it's hard to see. You probably want to rely on your knowledge about, the quantitative information, which is the lambda and your eigenvectors. That will be more reliable. Okay. In this case, we can easily see this is going to be a sink, because from the complex point of view, it's a sink. Meanwhile, in the direction of the real, it's also a sink. All right, so that's what we're going to do for high dimensional cases. These are 3. What about 5 dimension? You can imagine what's going to happen. One real repeated for 5 times. Maybe, 3 distinct real. And then another one real repeated for twice. Okay, maybe you can have one complex, two complex, a pair of complex, 3 distinct real, or maybe 2 distinct real and 1 real repeated for twice. Take it back. 1 real and another real repeated for twice. You may also have 2 by 2, so 4 complex, which means 2 pairs. So in 2 direction, it's going to be rotating. In the other 2 directions, it's also going to be rotating, but then 1 real. You may even have a 0 eigenvalue case. So you have so many more cases, but really what you need to focus on are just the following information. Number 1, lambda. Number 2, eigenvectors. That's it. That's the only 2 things you have to rely on. And as far as we know in linear algebra, there is really no restriction on how many dimensions your matrix can have. Even if you give me a 10 by 10, I can find eigenvalue and eigenvectors. And even though it's impossible for me to draw a 10 by 10, or even a 4 by 4, right? Or even 3 by 3 is hard to recognize, to look at. But the analogy still works. The same idea still works. You just need to focus on, do you have real? If you have real, you have straight line solution. If you have a straight line solution, you have a sink or source depending on lambda is positive or negative. Do you have a repeated real? Do you have 0 real? And finally, do you have complex? And if you have complex, focus on the real part to tell you spiral source or spiral sink or a center. That's roughly what will happen in high dimension. You need to rely on algebra because geometry will give you the sense, the understanding, the meaning of it, but it's really impossible to draw in high dimension. All right, that's how we do it. Of course, if you wonder applications, in which universe do we care about, ODE system in higher dimensions? Well, we can easily give you some examples, and you can probably make your own. That is, number 1, you have multiple species. You want to see how they interact with each other. So it's like predator-prey plus a cooperation plus predator and 2 prey, 3 predator and 5 prey, and they have all kinds of relationships between them. Okay. Second, if you think about SIR, that's already 3 dimension. SEIR, that's already 4 dimension, adding another exposure. So with other models, as long as you increase the number of variables who is involved, who is changing, whose behavior can be described by an additional differential equation, you are going to have higher systems. Something with extremely high dimension, weather prediction, where maybe you have to track, I don't know, track 23 or maybe 300 variables at the same time. So very easily, your differential equation actually grows really into high-dimensional cases. Number 4, we're not going to talk about the details, but a lot of PDE, partial differential equations, can be transformed into high order ODE. Okay, that means if you want to solve for a differential equation in for high order partial differential equations, sometimes people will transform them into high order ODE and solve it, because if you have a linear ODE, it's pretty easy to solve it, theoretically, of course. When you have so sometimes it is worth doing to transform your PDE into ODE, even though it means high order. But all I need to do is just increase the size of my system. Okay, so sometimes it's worth doing. Of course, if the dimension is too high, it's still difficult for us to use computers to simulate the solution easily. So this is one possible approach, but it's not a universal or uniform one-solves-all approach. All right, that will be all for the ideas of higher dimensional system. We're not going to do it in exams or anything. It's just purely for you to get into it and try to read more and roughly have an idea of how to analyze it. Seems like we're spending a lot of time on two-dimensional system, which is relatively simple. But actually, for higher dimension, they can be solved in exactly the same spirit. That is eigenvalue and eigenvectors. Up to now, I think you can finally answer the question that is, why are we spending a whole chapter in linear algebra learning eigenvalue and eigenvectors? Maybe the first time you do it, you kind of feel like it's interesting, but I want to see some applications, and the applications is exactly here. Basically, the majority part of the work when you're trying to solve for ODE is trying to play with eigenvalue and eigenvectors. Of course, for linear systems with constant coefficient. Okay, even for linear systems without a constant coefficient, you can still somehow study the eigenvalue and eigenvectors, where your A actually depends on T. Okay, and even for nonlinear systems, sometimes we still use the similar kind of analogy if you can locally approximate the nonlinear system with a linear system. So a majority part of the differential equation course is focusing on this eigenvalue and eigenvector. So it's pretty important if you admit that differential equation is pretty important. All right, that will be all for today, and that will be all for chapter 3.